Good afternoon, everyone. Let's get started. So last day we introduced the concept of pseudopotentials. So this is really due to the core electrons make the wave function very complicated, and to sort of really simulate the situation, we need a lot of plane waves, and that adds the computational cost. So in order to capture the valence electron behavior, we introduce this pseudopotential, where the potential is the same for the valence electrons, but it's no longer correct for the core electrons, right? So the goal is to make the wave function smooth so that we can use a much less number of plane waves to construct our wave function, all right? Okay, so it works pretty well for the materials. All right, another issue here is to use periodic supercell. All right, because of the periodicity of the system we deal with, so many of the first principles computer codes, such as ABINET, BASP, CPMD, or quantum espresso, especially quantum espresso and ABINET, they are open source codes that are free for academia. So they became pretty popular for materials research, right? So in these codes, the plane wave basis is used, right? So basically, a periodic boundary condition is always applied in these systems. All right, so the issue comes up, what if you have a finite system that is non-periodic, okay, like nanostructure, for example, a carbon nanotube. Right, so we play the same trick we did before when we performed the lattice dynamics calculations with GALP, because GALP also uses periodic boundary condition all the time, right, for all systems. All right, so for these systems, you can construct a large supercell with a vacuum, so that make sure that your finite dimension is kind of having a large distance between your dimension and the boundary. So we leave some vacuum for the finite dimension. All right, so basically when you put this domain in periodic boundary condition, which means you replicate the structures, then they will not interact with each other, okay? So for carbon nanotube with free boundary condition or isolated carbon nanotube, you can construct basically a carbon nanotube array, but leave enough space between the tubes so that the tubes do not interact with each other. So in this way, although you really simulate a carbon nanotube array, but because they are far enough, the properties you get will still be that for an isolated carbon nanotube, right? In other situations, you may want to purposely investigate the coupling between tubes, right? If you have a real carbon nanotube array where they are close to each other, right? In that situation, you should reduce the vacuum space so that the carbon nanotubes start to have interactions between each other, right? So that's going to affect the band structure, actually. You can try this if you are interested. Okay, so then what about the solution process? So how does it look like? Because this is a Cauchy algorithm that we will use a density to represent a property, and then we say that one density corresponds to one unique property of the system, right? So we need to have an initial condition. We need to initially guess some density, right, based on although you have a periodic system, you have some knowledge about the orbitals, right? So start with some guess of the density of electrons. Then we can calculate the effective potential, right? So we can use LDA or GGA because the LDA, the potential depends on locally on the density, and GGA also involves the gradient of the density you initially guess, right? So with the density, you can get the effective potential. Now with that potential, we go ahead and solve the Cauchy equations. So the Cauchy equation is shown here, right? So we said that this Cauchy potential is no longer the original potential, and the wave functions are no longer the original real wave functions. But anyhow, once you have this Cauchy equation, you solve for the wave functions, the dressed wave functions, and the wave function square then sum up from all the electron state. They recover the true density. Okay, although the wave functions are not the original interactive wave functions among electrons, but the density is correct. Okay, that's the whole idea about density functional theory. So we calculate the density from the wave function and check whether the density is similar with our initial guess. Right? Of course, the first iteration it won't likely give you the good converged density. All right. So usually it is not converged, so it's not self-consistent. Okay. Then you based on the density you get, you correct your initial guess, right? Or you can use your new density as starting point and run the loop again, right? After many iterations, the density will become close to the input density you use, right? Then you can set a tolerance, and once you kind of the error becomes less than the tolerance, we consider it to be self-consistent and convergence reached, right? Then we can record our output. Right, the output will include the total energy, because energy is an eigenfunction of, or eigenvalue of these Cauchy equations. And the wave function, I mean these Cauchy wave functions, right? And the eigenenergies, you can plot the band structure, okay? The band structure of different electron states depend on their wave vector, right? As well as the total energy of the system. All right, so for real band structure calculation, we also need to optimize the geometry, because usually the starting geometry is not optimized. Although for any geometry, for any given geometry, you can calculate wave function. That's not a problem. But when we talk about band structure, we usually refer to the band structure as at the optimized lattice structure, right? So we can do additional step for that. Okay, for material, we need to choose a pseudo-potential for most materials and the corresponding functional, right? Whether you want to use LDA or GGA, you need to decide on that. Okay, we have an initial structure. So with that initial structure, we will do a key point grade convergence test. How many key points we need, right, to have the results converged? Also, kinetic energy cutoff test, what cutoff energy we need to use. So these needs to be tested and see the convergence. And with that, we can calculate the total energy of the system, right? So optimize the geometry, which means that we're going to vary the lattice constant and see which structure has the lowest total energy, right? We have done that using lattice dynamics, using empirical potentials there. But here we can do this quantum mechanically without those empirical potentials, right? So you can vary the lattice constant as well as internal coordinates, right? Achieve the lowest energy, and then we optimize the geometry. On that geometry, now we generate wave function. Okay, by the way, in the geometry optimization, I mean a lot of self-consistent cycles will be done there, right? The previous slide we showed the loops will be run here, for each lattice constant and each internal coordinate. When you count energy, you will still need to do the self-consistent iteration, right? And once that is done, we will generate the wave function at the optimized structure. Okay, again, the self-consistent cycle will be done here. So once you have a wave function, you can calculate eigenenergies at the high symmetry k points, right? For the different energy levels, for each wave vector, there are multiple energy levels corresponding to the same wave vector. So, you know, even from the chronic penny model, we have seen that, right? So for 3D, we plot the high symmetry key points, then that's the band structure. Okay. So, what about the convergence criteria? You know, how do we know it's converged? There are a few criteria you can use. In Abinit, for example, it could be the total energy. So this TOLDFE sets a tolerance for absolute difference of total energy that, you know, if it reached twice successively, will cause the self-consistent function cycle to stop, which means that you know, if consistently the tolerance is smaller than the tolerance you set, you can stop the calculation and consider to be converged. For example, we can set 1 to the 10 to the minus 5 or smaller Hartree. Okay, Hartree is a energy unit used by chemists. You know, most often. So 1 Hartree is a 27.211 eV. All right. So when you set 10 to the minus 5th Hartree, this kind of is a very small energy number. Okay. All right. A different criteria you can use is TOLDFF. So this quantity sets a tolerance for difference of forces. Okay, so the forces is expressed in terms of a Hartree divided by Bohr. Okay. Again, if it reached twice successively, will cause the SCF cycle to stop. Okay. For example, you can set the value 1 order smaller than geometry optimization. All right, like 5 times 10 to the minus 6 Hartree Bohr. Okay. There are other convergence criteria. For example, TOLRFF, this is the relative difference of forces. And TOLVRS is the tolerance on potential residue. Okay, potential, the V, potential energy, right? And, well, not potential energy, actually the interaction potential V we use in the Cauchy equation, right? Or the TOLWFR is on the wave function square residue, okay? So how different the wave function is from the last cycle, right? So actually all these convergences are aimed at the same goal, or you can say they are equivalent, right? Once you reached convergence for energy, you must have reached convergence on wave function as well, because they're all dependent on each other, right? I would say the wave function is probably the most fundamental quantity. The energy, potential, the lattice, the forces all depend on wave function. So you can say they are all equivalent as long as you choose the number corresponding to the similar precision. So only one of these convergence criteria is needed, right? You don't need all of them. So total energy is very convenient. So I guess I think most people use the total energy for the purpose. All right. So now we have kind of introduced you the basics. You can perform a band structure calculation. All right. So we're gonna again share with you the code as well as a tutorial how to run band structure for silicon, and you're gonna have a homework problem calculating the band structure for gallium arsenide. Right. Gallium arsenide is an important electronic material. So the band structure is of great interest as well. All right. Okay, other than that, so what are the capabilities of ab initio calculations, right? We can use ab initio calculations to do a lattice dynamics calculations without using empirical atomic potential, right? So we already introduced to you that the empirical potential has a quantum mechanical nature, right? Now, once we know how to calculate wave functions, we can get the energy in terms of as a function of the distance of atoms, right? So so this can be done without those interatomic potential anymore. Okay. Well, this can tell us the nature of bonding, right? You have a homework problem, in the next homework to develop this potential for a molecule, hydrogen molecule, we discussed, right, at the beginning. Hydrogen molecule, we cannot solve it analytically. Only hydrogen atom we can solve analytically. Hydrogen molecule, you have to use numerical method. So you're going to have a homework problem, developing the interatomic potential for hydrogen molecule, right? So based on that potential well, you are able to judge the nature of bonding, right? Whether it's a strong bond or it's a weak bond based on the bonding energy. Then we can also perform the geometry optimization and the single point lattice energy calculation. Everything we can do with the empirical atomic potential, now we can do it with these ab initio calculations, right? And we can calculate Bach modulus, elastic constants, phonon dispersion, and the density of states. Of course, these calculations will be much more expensive than the classical lattice dynamics or MD simulation, right? Because we have to solve the Schrödinger equation. Schrödinger equation is more complicated than Newton's second law of motion, right? I mean, everybody knows that. Okay, so that's the lattice vibrational properties. Then we can certainly calculate electronic structure or band structure, either molecules or solids. Okay. So other than that, we can also predict the transport properties. Transport properties are more complicated than the electronic structure because they are based on the electronic structure, and we'll need to use some perturbation theory. So we're going to go through the methods later on how to do each of them. For example, we can calculate electron-phonon coupling and the electrical conductivity, because the carrier mobility and electrical conductivity is fundamentally limited by electron-phonon coupling. Right? If there is no electron-phonon scattering, the electron will move without any resistance. Right? You have a superconductor. So electron-phonon coupling is something that people working on superconductivity care a lot. So as the community for electronic devices, right? The carrier mobility and electron conductivity, we can predict those. Optical properties, depending on which optical bands you are looking at, then these properties are due to different mechanisms, right? So for the visible, usually is electron transition, interband transition, and electrons will need to be excited for absorptions there. In the infrared, it depends on whether you have metal or dielectric, right? If a metal, then there's a free electron oscillation. If it's a dielectric, it's going to be a phonon absorption of those photons. But anyway, eventually you want to calculate the refractive index of the material and absorption coefficient if the material is dispersive. Okay, this can be done with ab initio calculation. And the thermal conductivity. Okay, thermal conductivity, last time we introduced Boltzmann transport equation, right? So with the band structure, with the phonon dispersion, you calculate it using ab initio. You can get group velocity and specific heat, no problem. So the quantity that is left to be predicted is a realization time or scattering rates, right? So ab initio calculations can help you predict phonon scattering rates, and you can put in the Boltzmann equation to get the thermal conductivity, right? So there are ab initio molecular dynamics, right? You can run MD actually not based on empirical potential, but using the quantum mechanical calculation that can allow you to look at chemical reactions, all right? So it's very powerful, but also pretty expensive, right? Okay, so this is an example about band structure. So this is a lattice structure of silicon, right? It has a diamond structure. and this is the band structure. Okay, so in the tutorial, we're going to generate this band structure following the instructions there. And you can see that this is an indirect band gap material because the valence band top is at the gamma point, where the minimum of the conduction band is near the X point, right? So they are not at the same wave vector. And the band gap is about 1.1 eV, right? So that's why kind of silicon is a good solar material. 1.1 eV can harvest in the majority of the solar energy photon energy band. Right? Okay, this is another example. We can even visualize the wave function. Right, once you have energy levels, where you can pick any point on the band structure, and you want to realize the wave function, you can do that. Right. So this is an example of a titanium doped sapphire. Sapphire is an ultra fast laser material, right? We know the laser material when it is excited or when it emits photons, there's a transition between two energy levels, right? So these are the two energy levels, right? One is the ground state, the other is the excited state. So it tells you that after the transition, how the wave function of an electron will look differently. So these are actually the transition between two 3D levels, right? This is the titanium. Really, the energy level is mainly due to titanium dopant. So this is a transition between one 3D level to another 3D level. You can see the wave function has a lot of the 3D orbital shape with it. But also with some of the host atoms, not just the titanium, but with some wave function of the sapphire, which is silicon dioxide, right? So this tells you that after transition, how the wave function will be different, and because of different wave function, the bond length will change a little bit. Okay, usually the excited state. When you are at the excited state, electrons, on average, they are farther away from the nuclei, right? They're going to push the bond length to be larger, right? The ground state, electrons are closer to the nuclei, and the bond length will be a little bit smaller, right? So with this wave function, and you can understand how the structures are affected by the wave function, right? Okay, so next we're gonna. So those are the first principles calculations on static structures, right? Now we can look at, we already introduced you that you can do lattice dynamics calculation using first principles. We can even do molecular dynamics, right? How does this work? Okay, there are a few papers too you can look at. There is a classic paper by Carr and Paranano. They were the inventors of a CPMD. Okay, they were pioneers of combining the first principles calculations and MD simulation. All right. Then actually another paper from our own group, we did non-adiabatic MD simulation. That kind of you can look at electron transition in an MD simulation, which is a pretty special topic. All right. Okay, how do we do ab initio lattice dynamics calculation? For lattice dynamics, we need a dynamical matrix, right? That's all we need in order to generate the Furlong, eigenvalue and eigenvectors. So for the ab initio calculation to be able to run lattice dynamics, we need some perturbation, right? We call the density functional perturbation theory. It's not just a simple density functional theory. So perturbation, which means that we need to change the system, some way for Furlong calculation. Now, for lattice dynamics, the perturbation is really we displace the atoms in order to get the spring constants, right? So, okay, For a certain structure, we can get the total energy of a crystal, right? But that won't tell us the spring constant. In order to find the spring constant, we have to, pull the atoms a little bit and see how much energy will change, right? That tells us the spring constant. If you don't let the displacement happen, a typical DFT calculation can only tell you the total energy, right? It doesn't tell you how strong the bonding is. So we need to do a 3n independent displacement, which means on each atom, we need to displace the atom along x, y, and z, right? We can displace one at a time and observe how much energy will be changed. Then use a finite difference idea. We take a derivative, and that will tell you what the spring constant is, right? So with 3n independent displacement, and you calculate 3n different energy, we can find out the 3n spring constant. For each atom, there is a spring constant along x, y, and z directions, right? And we have n atoms, so there are 3n spring constant. And we can construct the spring constant matrix, right? With all those spring constant, now for any wave vector of phonons we look at, now we can create the dynamical matrix, right? So with the dynamical matrix, we can do a direct diagonalization and find the eigenvector for this dynamical matrix. And those are the phonon frequencies and the phonon eigenvectors, right? Eigendisplacement. So that will allow us to plot the phonon dispersion, right? So this calculation is more expensive than just a standard DFT because we need to run 3n standard DFT, right? After each displacement, we run a standard DFT calculation, find the energy, and then that's the finite difference idea follow. Okay, this is arbitration lattice dynamics, and these are some examples. For most of crystals, you can certainly use this density function of perturbation. It is not, although it's more expensive than the lattice dynamics based on empirical potentials, but this is still much doable. Okay, it's a matter of, it should be done with less than an hour or so. Okay, so this is what the sodium chloride. This is a single wall carbon nanotubes, and you know that the dispersion is fairly complicated. Some of you have chosen CNT in one of your homeworks to look at the dispersion with the tensor potential there, but now you can also do the density function of perturbation theory, and this dispersion relation will be more accurate than the tensor, right? Tensor is known to overpredict the cutoff frequency, right? The highest frequency. This height should be 1600 centimeter minus 1. Right? Now these are graphene, infinitely large graphene sheets, and we have we have 2 atoms per pyramid cell, so we have 6 branches. As you can see, the dispersion has 6 branches, right? For each wave vector. Okay, so that's a lattice dynamics. How do we run AMD simulation using first principles, right? Now we need to let the system move, right? So if the nuclei are also moving, then what's the total energy or total Hamiltonian of a system, right? In motion. Okay, so the total Hamiltonian now we need to still have the electronic Hamiltonian, which is the last term. That includes the kinetic energy for electrons, the external potential between the electron and the nuclei, and this is a Coulomb interaction between electrons, and this is exchange and correlation interaction between electrons, right? Then we need to add two terms to represent the nuclei in the system. Okay, the first is the kinetic energy for the nuclei. And the second term is potential energy for the nuclei, the nuclei-nuclei interaction, right? Okay. So this is total Hamiltonian. Now what about the total energy? Right, total energy now, in addition to the electronic system energy, we have the kinetic energy for the nuclei. Now nuclei, because their mass is pretty large usually, we can use the classical picture for the kinetic energy, which is a half mv squared, okay, summation on the nuclei, right? So this is still a classical picture of the kinetic energy for nuclei. And the potential energy for the nuclei is due to Coulomb interactions, right? So we have the summation from I from 1 to n, and j larger than I, then is a Coulomb interaction between the nuclei. Ri minus Rj is the magnitude, is the distance between two nuclei, right? So this is potential energy due to nuclei-nuclei interaction, and all the rest potential energy of the system is in the electronic system, right? So we can write in this way, so the first term is the kinetic energy, and now the second term is the nuclei-nuclei potential energy plus all the electronic energy that goes into the potential energy in the MD system, right? Now we're trying to build one-to-one correspondence between classical MD and ab initio MD, right? In ab initio MD, so the potential energy in the classical MD includes actually the potential energy between the nuclei, actually includes the kinetic energy of electrons, all right? So this is interesting. The kinetic energy of electrons in the ab initio calculation is actually part of the potential energy in the classical MD simulation, right? Because in the classical MD, we do not explicitly deal with electron-electron interaction, or there's no explicit electron degree of freedom there, right? So all the electrons are lumped into the potential energy in the classical MD, right? Okay. So for example, when you stretch a bond, right, the potential energy in the classical MD will change, right? And actually, that change is due to many things, right? Is certainly the nuclei potential energy will change, but all the electron, each term will change due to the distance of the two nuclei are different now. That will affect your wave function. So all these terms will be different, right? And all these 5 terms now together will be reflected in the potential energy in the classical MD. Okay? So again, the wave function and the electron density is a function of the nuclei coordinates, right? And those effects all enter into the potential energy of the classical MD system. Okay, so what's the flow chart of an ab initio MD simulations, right? Okay, now when you run MD simulation, we again need a certain initial configuration and the initial velocities, right? So they are there. But then we need to calculate the forces so that determine the acceleration and determine their velocity and the next position, right? So we do this using the empirical potentials in the classical MD. But what about ab initio MD, right? Now here, we don't know the forces directly, but we have to calculate the wave functions and the total potential energy for this configuration, right? And just to get the potential energy and the wave function, again, we need to run many SCF cycles, right? The previous, for a static standard DFT calculation, I mean, this will be done here, right? We get the energies. But we still don't have the forces yet, right? Now, the forces, then we have to do the perturbation idea, right? We have to, for that configuration, now let's move each atom a little bit along each direction. So we need to do that for the 3 n atoms, actually. And see how this, and then recalculate the total energy, right? And by performing this derivative, we get the force on that atom along each direction. So this step is very expensive. which means that you need to do many standard DFT calculations in order to get a force on each atom, right? And with that, the acceleration will be calculated. And so we use sort of the standard AMD algorithm, leapfrog, for example, to determine the next position and the new velocity of these atoms, right? So with that, then we rerun the loop and calculate the energy and do this perturbation, 3n perturbations, in order to find the forces. So we let the system go. Okay. So this type of ab initio MD simulation will take maybe 5 orders of longer time than the classical AMD, right? Because the evaluating of forces is so time consuming. But this is good for systems where you don't have any empirical potentials available, all right? And this can be run on any material, right? Also is a new material, for example. Okay, so this kind of ab initio MD simulation can also be used to look at electron-phonon coupling in molecules, right? We're going to talk about electron-phonon coupling in solids in much more detail later. But for molecules, we can look at the electronic structure. And the DFT will be able to tell us what is a HOMO, what is a NUMO, and what's the energy difference between the two. For example, if we look at our oxygen atom, right? We know that this HOMO is a occupied energy level, and the LUMO is the unoccupied, lowest unoccupied, right? So what is electron-phonon coupling in these kind of molecules, right? What does that mean? I can give you one example, right? There's not really phonon in molecules, but we can call them vibration, right? Some people will call it vibron. You can still decompose any vibration into the basic modes. We call them vibron, right? Okay, quantum dots, for example, they are kind of artificial molecules, and these are used for solar cell application, for LED and other applications, all right? And we need to understand the electron-phonon coupling, because the electron-phonon coupling is the mechanism that generates heat in these systems, right? So what is electron vibration coupling in these systems, right? First, we need to understand the electronic structure, right? So you can use codes like quantum espresso or so to calculate the band structure of the quantum dot, and you will get the discrete energy levels. Right? For example, this is an 8 atom, and this is a 32, this is 88, and if you reconstruct the bulk system, it's going to show the continuous band structure type of thing. But for these finite molecules, they just show different discrete energy levels, right? So for these kind of quantum dot, while the band gap is around the 0 eV, or you can say that the energy level below 0 is the HOMO, and energy level above 0 is a LUMO, right? And you can see for the small size of this quantum dot, the energy gap is large. And when you increase the size, the energy gap between the HOMO and the LUMO, it decreases, right? This is the quantum confinement effect. So that's why for quantum dots, even the same material, different size will emit different color, right? Indeed, if you use quantum dots for LED, you can easily control the color of light they emit by the size of the dots, right? Okay, so that's electronic structure. Then what is a electron vibration interaction? Okay, the vibration is basically you need to let the system move, right? Well, by the way, these electronic structures are calculated when the structure is static, or it's at its lowest energy configuration. Now, once you increase the temperature to a finite temperature, system will, all the atoms will move, right? And now you can imagine that for each unique configuration, the electronic structure will be different, right? or in other words, at each time step, the system will have a different electronic structure, right? So in other words, you can imagine that the band structure is not really a static quantity. As the system vibrates, the band structure is also time dependent, right? The energy level will vary with time, right? One electronic structure will correspond to a specific configuration, specific time-dependent configuration. All right. So when I imagine this quantum dot, not just the atoms move, also the band structure oscillates with time, right? Okay. So that oscillation tells you a lot of information on the electron vibration coupling. Okay. Now, if you plot the normal energy as a function of time, you're going to see it's going to vibrate, okay? Because you can calculate band structure for each configuration. You can see the energy level will be different, every time. So there's oscillation. The energy level, normal and the HOMO, they will oscillate as a function of time, and they oscillate for a different amount at the different temperature. Certainly, when we go to higher temperature, 501 Kelvin, the oscillation is much more intense than 63 Kelvin, right? Okay, so now if you perform a Fourier transform, right, from the time domain to the frequency domain, you can find out that the spectrum of this energy level as a function of the frequency. This tells you how strongly the electron energy level will couple to a specific vibration frequency. Okay, this normal tells you that actually electron couple very strongly with a vibration mode near 50-60 centimeter minus 1. All right. It might be that you have a lot of phonons available there. I don't quite remember here. It could be that you have a large phonon density states there, so that a lot of phonons available to scatter your electron. Okay, but the idea is that it's basically how the electron energy level is sensitive to the lattice vibration. Right? If you have a material where the system vibrates, but the energy level maintains a constant, okay, that system will have very weak electron-phonon coupling. That means that when the phonons are excited and the atoms move, electron is not sensitive to that motion at all. Okay, that's very weak electron-phonon coupling, right? Actually, that's the case for a lot of laser materials, right? Like titanium sapphire. That material is chosen as a 5 millisecond laser material. If you do a calculation, let the system move, energy level is very insensitive to lattice vibration because basic energy level is shielded, okay, by some of the 3D electrons are shielded by their 4s electrons, right? Okay, so that material has a weak electron-phonon coupling, right? A lot of other materials have pretty strong electron-phonon coupling, like for the solar cell materials, right? And you want to think about how we can either look for new materials or engineer the nanostructure so that we can make the electron-phonon coupling more difficult, right? Okay, like this quantum confinement is one way to do it, actually, because if the material is bulk, right, the curves are continuous. So you can find any phonon energy to make a transition, electronic transition, right? But for the quantum dots, the energy levels are discrete, okay? Now, in order for this happen, electron-phonon coupling to happen, your phonon energy has to match the exact energy difference between the two levels. So that kind of pose more restrict requirement on the energy conservation, right? So indeed, in quantum dots, we find that electron-phonon coupling is weaker than in the bulk material, okay? But the idea behind this electron-phonon coupling is basically how sensitive your electron band structure to the lattice vibration, right? Okay. We're going to look at that idea later for solids as well, all right? Okay, this is another example. We can use arbitrary MD to look at the chemical reaction, right? This is a dissociation of ammonia on the ruthenium catalyst. Okay, the ruthenium catalyst can help us to split ammonia, right? And you can see that you can run arbitrary MD. Right? You see that one hydrogen atom kind of leave the ammonia molecule, right? That means the dissociation happens. For this chemical reaction, we don't need any empirical potential, right? For the classical MD simulations, there are some potentials are able to do the catch the bond breaking, bond forming, like the Ribot potential, reactive bond order potential there for carbon, for example, right? But you can do this with a arbitrary calculation to simulate chemical reaction. This is another example that actually we did a little bit quite many years ago, is look at the reactions of lubricant additive, right? How they protect the metal surface, really. Okay, I mean, this is sacrificial molecules. So this is a additive molecule, right? Pretty complicated structure. There are two sulfur atoms, right? And how does it protect iron surface? Okay, this is a molecule at the room temperature, and if you put the molecule above the iron's surface at room temperature, nothing will happen, right? This is normal because the lubricant additive really supposed to function at high temperature when the combustion have, like an internal combustion engine, high temperature, how it protects the surface, right? So when you increase the temperature to say 700 Kelvin, which is a part C here, you can see that the molecule start to react with the iron substrate. Specifically, the sulfur atoms, they form bonds. Okay, but they still have bonds with the other parts of the molecule, so it's not totally broken yet. But when you further increase temperature at 900 Kelvin, right, which is the case D, now you see that the sulfur will break bonds with other parts of the molecule, and they form bonds with the iron surface. So, the other parts, basically now the molecule is sacrificed, but we form a sulfur on the surface that can, this bond is very strong. It can start to protect the iron on the surface, right? So you can see that we can sacrifice the additive molecule, but not sacrifice the metal surface itself. This is how these lubricant additives they work at high temperature, when the combustion happens. All right. Okay, so the benefits of performing this ab initio MD simulation, right, is really for systems where we do not have empirical internal atomic potentials. We certainly the AIMD is the only choice to perform MD simulation. Right. Also, the ab initio MD simulation is more accurate than the classical MD because the forces and energies are all evaluated using quantum mechanics. So the many body effects are included inherently. Remember that the empirical potentials used in classical MD, they are only approximations of the interaction. Right. So here I would say that in terms of quantum mechanics, it is exact. Forces and energies. Right. Okay, also compared to classical MD, where we do not really have any explicit electron degree freedom there. Now in the ab initio MD, we have all the electron information, right? So we have the time-dependent energy levels or the band structure, and that will allow us to even look at electron vibration coupling for our system, looking at the let's say the electron decay or electron carrier mobility and other information that is not in MD, okay, in the classical MD. Yeah, but the main limitation of AIMD is very expensive, right? It's several orders of magnitude longer than classical MD. So for classical MD, we have seen that we can perform calculations even on billions of atoms, right? You have a large enough computer. But for AMD, the maximum number of atoms you can do is probably a few hundred atoms, right? Yeah. Beyond that, basically with the computational power we have currently is forbidden, right? So for atoms from a single molecule to multi-molecules to a small, like a supercell of solids, up to a few hundred atoms, I mean, this is doable, although it becomes really expensive at the large size end. Right. Okay, to address this computational cost challenge, we can have the so-called hybrid method, right? Hybrid methods, which is a mix of a classical MD and ab initio MD, right? For chemical reactions, for example, the active reaction sites you can treat using the density functional theory, but the rest of the system that do not have the reactions happening, you can still use classical MD, right? It's just like if you want to simulate phonon transport, you can bridge Fourier equation and the BTE, using Fourier for the diffusion transport part and the Boltzmann equation for the ballistic part. Okay, so here you can use classical MD and the ab initio MD for the efficiency. Okay. So with that, now let's look at how to develop empirical potentials for classical MD, right? Because for different systems, the AMD and the classical MD, they are still both useful depending on your application, right? So one use of the first principles calculations to develop the empirical potential that can be used in classical MD, right? To do a multi-scale simulation, right? Because the tensor potential and other potentials, the people developed them actually with the help of first principles calculation. Okay, so a few reference papers, the Tarsov's classic paper on how he developed the tensor potential for silicon, and we have a paper that developed a potential for bismuth telluride, and there are other papers develop potential for nitrides and oxides and other materials, right? Okay, so why we want to develop potentials for classical MD? Because reliable interatomic potentials are still very rare for solids, right? I would say for most solids there are no potentials available. I mean, some of you try to run MD simulation for your material, and it turns out that no potential is available for that system, so you cannot run classical MD, right? Some of you already see that. So first principle calculation can help you to develop those potentials, although it is pretty, I would say, tedious and pretty risky. That's why these potentials are so rare in the literature, right? Okay. Well, for many relatively new bulk materials, these potentials do not exist, right? I mean, there are new materials being synthesized by chemists every day, and nobody has really developed potential for those new materials yet, and it takes time, even it's doable, right? So that's for like a single material, and what is even more challenging is the interfaces, because now interface you can have two individual materials, and there are so many combinations, right? Much more combinations than just the number of single materials. So for those interfaces, the interatomic potentials are almost always not available. Okay, there are only a few available for the well-known interfaces or the prototype kind of interfaces. But that said, recently there are some new developments using machine learning. Right, so this machine learning potential is neither the purely empirical potential or the the ab initio type of interaction. It's somewhere in between. So we're going to introduce how these machine learning potentials are developed and how they're used. So this is a kind of a pretty emerging topic we're gonna cover later. All right, but let's say how we can develop this classical empirical potentials using DFT. So basically it's an inverse problem, right? It's an inverse problem. Now we know with empirical potentials, we can calculate a lot of properties. We can find out the equilibrium lattice constant, right? We can find out the bulk modulus and the elasticity constant, the elasticity tensor, as well as the phonon density of states and the phonon dispersion can be calculated. Also, the energy surface can be calculated. Energy surface means that for any unique configuration, you can calculate the single point energy, right? So this energy surface can be like infinite number of configurations you can do, and the infinite number of energy data points you can plot from the potential, right? So there's a lot of kind of redundancy in the data because empirical potentials usually have how many? Anywhere from 3 or 6 or 9 parameters in the potential, and you can generate many properties, right? Especially the energy surface, that can be infinite number of single energy points you can calculate, right? Okay, so to develop potential now is an inverse problem, right? We now have these observables, and how can we find out the parameters in these potential, right? As well as the potential functional form. So for a material, we usually know the lattice constant at the equilibrium, or the bulk modulus and elasticity constant. Maybe we haven't already measured the phonon dispersion using neutron scattering, or the phonon density of states together, right? And the energy surface is something that is hard to measure from experiment, but energy surface we can generate from the DFT calculation, right? The DFT, for any unique configuration, we can certainly calculate the band structure corresponding to that configuration, and also the total energy for the system, right? Okay, so this is an inverse problem. Now, that has been known for a long time, but conventionally, before the DFT become so practical to use, so only the experimental data were used to fit the potentials, right? So by that, the quality of a potential depends on the availability of experimental data and depend on their accuracy, right? Maybe different groups, when they measure the same property, they may, end up with different values. So we need to make sure that the uncertainty is considered there, all right? Okay, now with the developments of the DFT calculations as well as more powerful computers, we can generate the energy surface easily. Energy surface, again, remember, is a energy corresponding to one specific configuration. So energy surface means that we have many configurations, we have many energy. That kind of database is energy surface. All right. So with that, we can also take advantage of this energy surface to derive these parameters in the energy in the interatomic potential. But that depends on the accuracy of the DFT calculation on the total energy, right? So if we use DFT, then our accuracy of these potentials relies on the accuracy of the DFT. It cannot be better than the DFT accuracy, right? All right. So why we want to involve the density functional theory in the potential development? What's the limitation of the conventional method, right? Everybody likes experimental data for validation, right? Many people don't trust your data unless it is validated experimentally. But the limitations are like the amount of experimental data is typically not sufficient to generate a potential good quality, right? You can have a lattice constant, you can have a bulk modulus, elasticity constant or so. That might be 10 data points in total. But what if you have 10 unknowns or even more than 10 unknowns, right? Then that not even allow you to calculate even the unique solution. No need to mention some data redundancy, right, to have better uncertainty control. So the number of data points is pretty limited. And more kind of seriously, that those experimental data only correspond to the interatomic potential near the equilibrium, right? They do not usually touch the region that is far from the equilibrium. Okay, again, a lattice constant, usually you measure at the equilibrium, right? Those elasticity constant or so at near those are the probably near the equilibrium, right? But if you care about heat transfer, you need to consider the behavior a little bit away from equilibrium. Those are anharmonic effects, right? Those are anharmonic effects determining the phonon-phonon scattering rates and the realization time and the thermal activity, right? Now, for chemical reactions, it's really even farther away from the potential well, so you need to go long distance and to break the bonds, right? So that's far away from the equilibrium. Okay, those are not captured really in any of the lattice constant or elasticity constant, and because they are, far beyond the state that the material is about to be dissolved, right? Or bonds are to be broken. So that's why we need a lot of data away from the equilibrium, and ab initio calculations can easily generate the energy for configurations where we displace the atoms far away from equilibrium, right? Pretty convenient. Okay, so now how do we represent the total energy in DFT calculation, right? We already talked a little bit, from the ab initio molecular dynamics, but let's look at it again. So the empirical potential has a quantum mechanical nature. And so the total potential energy for the electronic system is, the four terms summed up. Okay. Now, for the system where we include nuclei, we also need to take into account the Coulomb energy for ion-ion interaction, right? Because in the single point energy calculation, the ion-ion interaction is also there. So we just simply add a term, the last term, where represent the ion and the J with atomic numbers Zi and the Zj, right? So this energy is added, and we need to sum up the pair interactions, right? Okay, so with the four terms for the electrons, this is the total potential energy for our atomic system. And this is the energy actually we can calculate from the DFT calculation, right? So now back to the classical potential in the lattice dynamics. The empirical atomic potentials contains usually a short range interaction and a long range interaction, right? Think about, for example, Morse potential or Buckingham potential. Maybe Buckingham potential has the closest similarity to the form we just see. So that the total energy is equal to the summation of the short range interactions, right, plus the long range, which is a Coulomb, right? This is what we did for the lattice dynamics total energy calculation, right? So now let's compare this DFT and the classical lattice dynamics. So the Coulomb part is calculated the same way, right? So in the DFT, the Coulomb, in the total energy, the Coulomb interaction is between ions is calculated using this simple formula. So the same way. So the DFT can only determine the total short range potential energy of the entire system, so that we can build this one-to-one correspondence between this is DFT and this lattice dynamics, right? So in the DFT, we have basically the entire system. We cannot separate these interactions to each pair. It's a multi-body interaction, right? So, but in the classical lattice dynamics, remember all the short range interaction you can sum up, right? You can take into account each pair interaction and add them all up. But a standard DFT calculation won't help you do that separation, right? It's for example, the nuclei interactions are no longer a pair, because they always consider that the 3-body, 4-body, and 5th body and the 6th body all included in the DFT, right? So it's just one entire energy for the system. Okay. But the right-hand side, right-hand side, we need to figure out the parameters because the Buckingham potential, for example, or the Newton-Jones potential, they have parameters unknown on the right-hand side, right? So we need a multivariable fitting process, which means that we cannot just run one DFT calculation and find out parameters. We have to do it for many different configurations, right? And that will give us the enough resolution to determine the potential parameters. Okay, so the first step is to select the potential form, right? Before you even talk about parameter, what's the functional form? So previously we talked about the different bonding, and each bonding can have a appropriate potential form, right? Newton-Jones potential for the van der Waals interaction. There are two unknowns for each pair interaction, sigma and the epsilon, right? There's a Morse potential. Morse potential has 3 unknowns in it. This is a D, there's an A, there's an R, RE, okay? The Buckingham potential has also 3 unknowns in it, right, for one pair. If you have multiple pair interactions for compounds, then the number of unknowns will be more than this, right? So if you want to include a higher the body interaction, then you can do it, right? You can three body terms, like in the Tarasov, they have the 3 body interactions, and for certain interactions you have 4 body, right? That can be included with more unknowns, right? That's fine. Okay, then to determine the fitting quality, we need to have define a quantity that measures the quality of the results, the sum of squares, right? So this F is equal to sigma from 1 to n observables. You have n observables, right? The Wi is a weighting function, and Fi observable is observed value, and Fi calculated is a calculated value, right? So a good quality of potential need to make sure that the calculated value is close to the observed experimental value, right? So the quality of a potential depends on how many observables you have, and you can assign different weighting function. Observables can be lattice constant, right? Can be elastic constant, bulk modulus, phonon frequencies, and energy, okay, for different configurations, right? So we want to minimize the square, okay? So how do we assign the different weighting factor, right? So if we fit to experimental data, the weighting factor should be inversely proportional to the uncertainty in the measure value. So this is pretty straightforward. Some certain measure values, can be more trusted, right? Less uncertainty, then we should give those a higher weighting factor. And if a observable measure you're not so sure, then we should give less weighting factor, right? Okay, another point is that the weight factor should be inversely proportional to the magnitude of the observable squared, okay? So because the observables have different units, have different magnitude, right? We want to sort of, when they enter into this square function, error function, we want them to be on the same footing, right? So for example, your lattice constant can be, usually is a few angstrom, right? So it's a single digit. But your vibrational frequency, you have a phonon frequency that usually a few hundred centimeter minus 1, right? So some F will be just a few nanometer, some F will be a few hundred centimeter minus 1. But you want them to have a similar role, so basically the weighting factor for those few hundred centimeter minus 1 should be much smaller. Otherwise, they're going to totally dominate over other observables, right? So this is a pretty straightforward too. Is just try to unify the different observables with different units and different magnitudes so that they contribute kind of uniformly to the error function eventually, right? Okay, so The conventional fitting methodology is that we have an experimental structure is known, and then we can vary the potential parameter. You can start with the initial guess of this potential parameter, okay? And you calculate the forces, and then minimize the force. If the force is not minimized, then you run the loop. But if the force is minimized, now you can reach equilibrium structure, right? Now you can check whether your equilibrium structure has the lattice constant as observing experiment, right? If it's not, you have to come back and change your potential parameter, right? And based on whether your lattice constant is over-predicted or under-predicted, you change your potential parameter and then rerun the simulation until that your lattice constant agrees with the observed. Similarly, this loop should be done for other observables. And after all of the observables have the values similar to the experimental data, of course, this is judged by this f function, right? You have different observables. Then we consider the system has reached convergence, and we have developed a successful classical potential, right? This is a conventional way. Now with DFT, we can add the potential energy surface into the fitting process, right? So the atomic configuration near the equilibrium is shown in this diagram. So the second configuration is the equilibrium, right? We have no displacement, so we know that energy will be the lowest. And if you displace one atom, the energy will be higher, right? We say it's here. If you displace 3 atoms, the energy will also be higher than the equilibrium, right? Excuse me. So we plot all this energy as a function of the configuration index. So we put this energy together, and you can see that maybe we see a formula like this. Now our task is to develop a classical potential that can fit to this DFT energy surface, right? So this diagram shows you that what if we choose Newton-Jones potential, right? E is a function of the distance. You might find out that, okay, we're not really able to exactly fit the original potential well, because that's pretty normal, because it's a multi-body interaction. And classical potential is only an approximation to the true interaction. So it may, it very often end up with that you adjust these parameters, and you can still only fit one part well, but not the other parts, right? So again, for thermal purpose, we care more about the equilibrium as well as somewhere away from equilibrium, but not too far, right? So we want to make sure that the fitting near equilibrium is the best. So you can see that it may turn out that when you go far away from the equilibrium, the errors become larger, right? Which may not so important for thermal, but this fitting may not be so good for chemical reaction, where you really care about the energy, near the breaking point, right? So in that sense, that because the fitting, you have to choose where to have a larger weight factor, and depending on your purpose. So one potential developed for one purpose may only be good for that purpose and not good for other property predictions, right? Because it's only an approximation to the DFT, right? In that sense, that the DFT has a better transferability, right? The DFT, the same kind of pseudo potential, same functional can help you understand both thermal, optical, and other properties. So it has a better transferability than the classical potential, which may only be good for one property prediction, right? Okay. All right. I think that's so much for today. Yeah. Thank you. Some of you already submitted both homework to me, and some submitted homework number 4. Right. Remember, you have another homework due on Thursday, and it should be okay. All right. Thank you.